Hi, my name is Liu Jia from the Hong Kong Polytechnic University. The reported topic is investigation of hybrid photovoltaic-wind system with battery storage for high-rise buildings in Hong Kong. The reported outlines includes 5 parts, that is, development of renewable energy and energy storage systems, experimental test of a photovoltaic and battery storage system, design optimization of hybrid photovoltaic wind system with battery storage for high-rise buildings in Hong Kong, optimization results and discussion, and finally conclusions. The renewable energy and energy storage system is experiencing an increasing development in recent years. As is shown in the left picture, the solar PV global capacity totaled to 627 gigawatts by the end of 2019, and China leads the market for 30.1 gigawatt in 2019. A comparable wind power is installed by the end of 2019 for 651 gigawatt, and also China leads the market of over 26.8 gigawatt. In terms of energy storage installations, the global market for energy storage of all types reached 183 gigawatt in 2019, and the majority of it is pumped hydro storage. Battery storage totaled over 3 gigawatt in early 2019, and we can see that a mixed result is shown for the leading market of battery storage, and over 500 megawatt is installed in US and China. The renewable energy and energy storage system is developing in high speed, and is very important for sustainable supply of urban cities. It is shown that over 60% of carbon emissions are attributed to the building sector in Hong Kong, while about 3 to 4% of renewable energy can be exploited until 2030 in Hong Kong. Hong Kong launched a Climate Action Plan 2030 Plus in order to reduce the carbon emission. So this study mainly aims to study the technical and economical feasibility of using renewable energy and energy storage system for urban buildings. Firstly, experiment of a PV and battery storage system under 2 typical energy management strategies, that is maximizing self-consumption and time of use strategy, is conducted to verify the chassis simulation model based on a testing platform in Hunan University of China. The system schematic of the PV battery system is shown here. We can see 30 PV panels are installed on the rooftop of the test building, and a 12 kilowatt-hour lithium-ion battery is equipped in the building. The tested energy management strategies is developed and input to the power management plant to control the power flow among the PV panels, utility-grade battery storage, and also building load. Here we introduce the tested energy management strategies. For the maximizing self-consumption as shown here, we can see when PV generation is available, it is firstly used to meet the load and then charge the battery and finally feed it into the grid. For the time of use strategy, is controlled according to the electricity price of the utility grid. For example, in valley hours, the grid power will be firstly used to meet the load and also charge the battery to full state of charge at a low cost. while in peak hours, the battery will be used prior to the grid to meet the load, because the utility grid is at a higher cost. The power flow and the verification result of maximizing self-consumption strategy is shown here. We can see that the battery is firstly charged by the surplus PV power, and then when PV power is decreased, the battery should be discharged to meet the load. We found that the tested and simulated battery state of charge has a maximum error deviation of about 0.03. And for the time of use strategy, it first experiences a peak period, and the battery should be discharged to meet the load. And then a flat period is experienced, and the battery will not be charged or discharged. And then valley hours happens, and the battery will be charged by the utility grid at a low cost to full state of charge. The maximum error deviation between the tested and simulated battery state of charge is about 0.04. And we can see that the experiment can validate the energy balance-based battery and energy management strategies. And we also know that the battery model and strategy model is independent of weather conditions and the locations. So we use the validated battery model and time of use strategy to study the renewable energy applications for high-rise residential buildings in urban area. Here, a typical high-rise residential building is adopted for the renewable energy application analysis. 4 typical cases is developed, and we can see that for case 1, the PV panel are installed in the rooftop and facades of the building, but it is not enough for the electrical load of the building. And for case 2, the wind power is introduced together with the PV power to keep a balance between the renewable supply and the electrical load. And for case 3, the battery is introduced to the hybrid supply to keep a balance between the supply and the load. And for case 4, both battery and wind is optimized to get a comprehensive technical and economical optimal solution. Both technical criteria and economic criteria are adopted as optimization objectives. For the technical criteria, 4 indicators regarding the 4 major components of the hybrid system, that is, renewable energy self-consumption ratio, cycling aging, load cover ratio, average grid stress, are developed. And these 4 indicators are normalized and integrated as a technical optimization criteria. To evaluate the economic performance of the hybrid system, the levelized cost of energy, covering the investment cost and also benefits, are developed. The investment cost includes initial cost, replacement cost, operational and maintenance cost, and also rescue cost. And while for the benefits here, the feed-in tariff, transmission loss saving and expansion saving, and also carbon emission savings are included for the levelized cost of energy evaluation. The non-dominated sorting genetic algorithm is adopted for the design optimization process. And here we can see in case 4, when both battery and wind is optimized, the integrated technical criteria and economical criteria shows obvious trade-off conflict. And the final optimal solution is obtained by the minimum distance to the utopian point method. And here the sizing result is shown. We also conduct a sensitive analysis to show the impact of battery capacity and the wind turbine number on the optimization indicators. For the first part, the optimization results and discussion is displayed here. Firstly, the power flow of renewable energy system in typical vehicle forecast is shown. We can see that the mismatch between the renewable generation and building electrical load is observed in case 1 and case 2. And the battery storage can increase the load matching and self-consumption performance of system to a large extent, which can be shown in case 3. And in case 4, we can find that the optimal PV wind battery system can cover majority of the weekly load. The monthly energy flow and load matching of 4 application cases is also shown here. We can see that the building electric load in summer is relatively higher than that in winter due to a large cooling load in the hot summer and warm winter region. The monthly load cover ratio is increased from case 1 to case 4, and on opposite seasonal difference on the load cover ratio can be observed when wind turbines are introduced in case 4 and case 3 and case 2 to case 4. And it is dependent on the wind power generation. Here, the annual average load cover ratio and the self-consumption ratio of the 4 application cases are compared. We can find that the load cover ratio can be increased from about 60% to 53% from case 1 to case 2 when the wind power is introduced, and the battery storage can cover another 14% of annual load in case 3 compared with case 2. And finally, the optimal case 4, covers majority of annual load of over 81%. For the economic analysis of the hybrid system, we can find that the initial cost accounts for the majority of investment, and the feed-in tariff in Hong Kong is very encouraging, and it gets the most part of benefits. And the levelized cost of the PV system is about $0.52 per kilowatt hour, and the minimum levelized cost is the PV wind system for $0.12 per kilowatt hour. And for the final optimal PV wind battery system, it's about $0.22 per kilowatt hour. Here we get the conclusions. The energy balance battery model and 2 typical energy management strategies of the PV battery system is validated by the experiments. And the PV system covers about 60% of the annual load at a higher levelized cost of energy, while the PV wind system has the lowest levelized cost of energy, covering about half of the annual load. The battery improves the annual average load cover ratio and self-consumption ratio by about 14% and 60% respectively. And the comprehensive optimal PV wind battery system covers over 80% of the annual load at affordable levelized cost of energy of about $0.22 per kilowatt hour. So this study suggested that the PV wind system can be applied in high-rise residential buildings in Hong Kong with a low levelized cost, and the PV wind battery system can contribute to higher building energy autonomy with affordable levelized cost. And the conclusions can provide a reference to facilitate the renewable penetration into urban areas. For further research, we also conduct a study on hybrid renewable energy system integrating with hydrogen vehicles. Here, the hybrid supply of PV and wind is adopted, and the lithium-ion battery is used as a stationary battery storage for the high-rise building. And The hydrogen vehicles are divided into different groups following different cruise range and schedules. It's used as mobile storage for the building. So the transport and building sectors are integrated to maintain a sustainable development for the urban area. Thanks for your attention.